Welcome back to The Deep Dive. We're the show that cuts through the noise to get you the insights you really need. Today, we are getting into something absolutely fundamental for railway safety, really the bedrock. How we decide which risks truly matter, and crucially, how we make sure the right resources are there to tackle them. I want to kick off with something real, something that, well, every safety pro needs to think about. Picture one of the world's most advanced, fully automated metro systems like the Dubai Metro. Amazing engineering, right? Built to move millions safely. But then in 2024, a small lithium-ion battery, probably from an e-scooter, catches fire and throws the whole operation into chaos. Now, if you're an engineer on that project designing this incredible system, how does a little consumer gadget, something seemingly so minor, nearly bring it all crashing down?
That is exactly the right question to ask. It really throws into sharp relief the challenge of, well, anticipating all the risks. And it really highlights the danger of maybe overlooking these newer hazards, especially things coming from, passenger behavior or consumer tech. It's a stark reminder that safety isn't just the big infrastructure. It's also about those tricky interfaces, the human factors. So our mission today is to really understand the formal, rigorous process that's specifically designed to catch that sort of thing early. It's called impact assessment. You might also hear it called criticality assessment, or maybe assessment of significance. Same thing, essentially. And look, this assessment, it's not optional. It's the absolute gateway. It's that first foundational step that decides the level of scrutiny a project needs, the resources, the expertise required, and critically, it defines the scope of the big safety plan. The formal document, the System Safety Assurance Management Plan, or SMEMP, this assessment sets the stage for that entire plan.
Okay, so this isn't just a project manager having a gut feeling like, this looks tricky, let's assign some engineers. This is structured, formalized, right from the very beginning.
Exactly. It locks things in. And for anyone listening who's maybe starting out in their career or still studying, here's the really vital distinction you need to grab onto straight away. The impact assessment at this early stage isn't evaluating the inherent risk of the railway system itself. Not yet. That deep technical dive, with APIs and FMECAs, that comes later. What this initial assessment is evaluating is the risk of having an insufficient project process. It asks, okay, given what this project involves, do we actually have enough time, enough expertise, the right management setup? Is the process itself robust enough for the challenge?
Wow. Okay. That's a subtle but really important difference. So you're assessing the risk of the plan being wrong, not just the thing being built. So what happens if that initial assessment says, nope, the process, the management, the funding, the timeline, it's just not good enough? What's the immediate fallout?
Well, the immediate consequence is serious. If the project process is deemed insufficient for the task, the entire project gets slapped with a critical classification. Right there.
Yeah.
And that critical tag instantly means more scrutiny, mandatory higher resource levels, often mandatory independent checks by a third party. Failing this early assessment, it can mean the project gets frozen on the spot, or you're forced back to the drawing board to come up with a much more robust plan, a bigger SMP, maybe even needing more senior engineers involved. It essentially locks in the safety budget before a single track is laid. That's why this step has so much weight.
Right. It forces the tough decisions early before you're too far down the road.
Okay, let's get into the nuts and bolts then. If this assessment is the gateway, what are we actually measuring? How do engineers take that nagging feeling, like the Dubai battery fire, and turn it into something, well, quantifiable? What are the dimensions of criticality? Okay, so we generally rely on 6 key dimensions. These are the main factors engineers use to gauge the, let's say, the size or the significance, the criticality of a proposed change or a whole new project. These dimensions work together to basically scope out the entire safety effort needed.
Makes sense. Let's take them one by one. Dimension 1, complexity. Railways are obviously complex systems, but how do we pin down complexity beyond just, lots of moving parts?
Yeah, complexity is much broader than just technical intricacy. We define it as, yes, the complexity of the tech systems and how they interact, but just as importantly, the organizational factors and the environmental ones too. Railway projects are kind of notorious for this, aren't they? You've got dozens of stakeholders, multiple technical disciplines, site-specific challenges. Just to give you an idea, some research on huge track doubling projects in India actually identified 7 distinct types of complexity. Things like organizational complexity, technological, environmental, cultural factors, infrastructure challenges, communication hurdles, and stakeholder management. You've got to look at all of them. High organizational complexity, say, trying to coordinate 10 different contractors smoothly that can bump up the criticality just as much as some cutting-edge, untested software.
That rings true. The failures often happen at those seams, right? Between contractors, between departments, not just inside the black box of the technology itself. Okay, dimension 2, failure consequence. This sounds a bit grim, but I guess it's the core reality check.
It is the ultimate reality check, yeah. We have to formally map out the whole spectrum of potential harm if something goes wrong. International standards, specifically EN 50126, they give us clear objective categories for this. It ranges from, say, insignificant, maybe a minor injury, doesn't need medical help, right up to catastrophic. And that means life-threatening injury or, tragically, multiple deaths. And this can't just be theoretical. The stakes are incredibly high. Just think about the scale. In 2023, in the U.S. alone, railroad-related deaths hit 995. That was the highest figure since 2007. That number, it's sobering, and it really underscores why assessing consequence is the absolute foundation for every safety decision that follows.
Wow, 995. Yeah, that really puts it in perspective. We're talking about protecting lives on a massive scale, not just avoiding a few minutes delay. Okay, let's move to new systems. Dimension 3, technology novelty.
Right, novelty is all about how mature the technology is, how established is it, how much real-world testing has it had, how proven is it. Because when you bring in something brand new, unproven, you are basically guaranteeing that you're introducing unknown ways it could fail, unknown failure modes. To try and manage this uncertainty, the rail industry uses something called the Rail Industry Readiness Levels Framework, RIRLs for short. It's actually adapted from NASA's original technology readiness levels, TRLs, but specifically for rail applications.
RIRLs. Okay, unpack that a bit. If someone isn't familiar with the NASA scale, what's the difference between, say, RIR1 and RIRLM9?
Sure. So the RIRLs give you 9 stages of maturity. RIRL1 is basically just a concept on paper, maybe some basic lab tests. It's pure potential risk, very high novelty. RIRL9, at the other end, that's technology that's fully proven in operational service. It's validated by tons of real-world data, often across different types of environments. So if you're proposing, say, a completely new type of sensor technology and it's only reached RIRL4, which means it's been validated as a component, but maybe only in a lab or simulated setting, your criticality assessment has to rate that much higher. Higher than if you were just installing standard proven track circuits that are definitely RIRL9. A low RRL number directly means higher criticality simply because you don't have enough operational data to accurately predict how often it might fail.
That sounds like a crucial reality check, especially with all the excitement around new tech. Okay, dimension 4 is reversibility.
Reversibility asks a really practical question. If this new system or this change fails badly tomorrow, can we quickly and safely switch back to the old way of doing things, to the existing system? Being able to roll back easily is a huge risk reducer. Think about the challenges they faced building the Doha Metro. It was the region's first big metropolitan railway. They didn't have an old metro system to fall back on if the new one had teething problems. So they had to build safety very carefully into every single phase of the rollout across all 76 kilometers of track, precisely because they lacked that fallback option, that easy reversibility, a system where you can't easily revert. That automatically pushes the criticality rating up.
Right, no safety net there. Okay, now for one that sounds like it could easily be missed. Additivity, or you call it the accumulation of insignificance.
Yes, and this is one that safety experts really stress because it's often behind unexpected accidents. You might have one modification, maybe a small software update, or a minor component change. On its own, it gets assessed as minor, non-critical, fine. But what happens when you layer lots of these small changes on top of each other? Say 10 non-critical tweaks over a couple of years. Well, they start interacting in ways you didn't predict, non-linear effects. And suddenly you have what we call emergent risks, major problems popping up from a combination of minor changes. So the impact assessment must proactively look for this potential pileup. It forces the team to step back, look at the whole picture, the cumulative risk, not just the risk of this one change they're proposing today.
That sounds tricky to spot, like death by 1,000 cuts almost. And finally, dimension 6, monitoring capability. Can we actually see a problem developing?
Exactly. Can we detect problems early enough? And can we actually intervene effectively before a failure spirals into something serious? If a system gives you absolutely zero warning before it fails, or if the only way to intervene is a massive disruptive shutdown with no notice, then its criticality rating has to shoot up. You look at modern systems like the Dubai Metro again. They use really sophisticated condition monitoring alarms, tracking temperature, vibration, performance glitches on safety-critical gear. That allows them to intervene proactively, often without disrupting service. So if your proposed change makes it harder to monitor something or introduces new failure modes that are basically invisible until they happen, that's a big red flag, high criticality.
Okay, so those 6 dimensions: complexity, consequence, novelty, reversibility, additivity, and monitoring, they're like the pillars holding up this whole criticality decision. And the crucial thing seems to be how they combine, right? It's not just adding them up.
Absolutely right. It's nonlinear. If you have, say, high consequence plus high novelty, the criticality doesn't just add up, it jumps exponentially. If even 2 or 3 of these dimensions push into the highest risk category, the whole project instantly gets bumped into the top tier of criticality. And that mandates the maximum scope for the safety plan, the SSMP.
All right, we've got the dimensions. Now, how do we translate this theory into practice? Let's walk through the actual steps involved in doing a criticality assessment.
Okay, step 1 is planning and scoping. And this isn't just ticking boxes. This initial assessment, it has to be done by someone suitably qualified. Usually a senior system engineer or a system safety assurance practitioner, an SSA expert. They need solid knowledge of the project and the relevant standards. And critically, the final assessment document, it has to be formally reviewed and signed off by the chief engineer.
And there was a key principle for this step, a sort of guiding philosophy. You mentioned being conservative.
Yes, absolutely. Because this impact assessment happens right at the start. Often before all the detailed design work is finished, you have limited data. So the guiding principle, the absolute rule, is that the assessment must always be conservative. When you're uncertain about a risk factor, you have to assume the worst plausible case, and you must clearly document all the assumptions you're making. It's always professionally and ethically safer to maybe allocate resources that turn out not to be strictly necessary later than it is to underplan and discover a critical safety hole mid-project.
I get the professional need for being conservative, but let's be real, doesn't that clash with project realities? Budgets, deadlines. How does an engineer actually defend saying we need more resources because we're being conservative when management is pushing back hard on costs?
That's the million-dollar question, isn't it? It highlights exactly why this document is so powerful. The defense lies in the requirement. It's about legal and regulatory compliance. By using those 6 dimensions, by showing, say, look, we have high novelty here combined with potentially catastrophic consequences, the engineer demonstrates that the resulting safety budget isn't just a nice to have, it's mandatory to meet the rules. If the assessment says this project is critical and needs an independent safety assessor, an ISA, and a bigger budget for specific safety tasks, then management generally has to find those resources. Otherwise, the regulator could halt the project. So the assessment document itself becomes the justification, the shield protecting that necessary safety spend.
That's a really strong point. The process forces the issue. Okay, step 2. Identifying project risk triggers. What are these? Are they like specific warning signs?
Yes, exactly. There's standardized indicators that flag potential criticality, often directly linked back to those 6 dimensions we just talked about. So for instance, a major trigger is technology maturity. If the tech you're proposing has limited operational data, no proven track record on failure rates, or it's sitting at a low RIRL level, ding, 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 alarm bell rings, that flags potential high criticality. We saw this with the Doha Metro, putting in one of the world's fastest driverless systems, hitting 100-kilometer runs. That immediately triggered high criticality because there just wasn't much precedent. That lack of maturity forced their independent safety assessor team to really account for those unknown failure possibilities. Another big trigger is complexity of change. High complexity just inherently creates more interfaces, more places where things can interact unexpectedly, more opportunities for unforeseen risks to creep in. Think about the sheer scale of coordination needed for something like Crossrail's Elizabeth Line in London. I mean, the project reportedly handled over 6,000 separate evidence submissions, design documents, safety reports, hazard records, all flowing between multiple interacting systems and contractors. That level of administrative and technical complexity is, in itself, a major risk trigger demanding a high criticality rating for the overall management process.
And those boundaries, the interfaces, that's where the danger often lies, as you said.
Absolutely. Interfaces are a huge trigger, whether it's the boundary between different technical systems or between different organizations like the track owner and the train operator, or even different software versions. These boundaries multiply the potential for hazards. The UK's Office of Rail and Road specifically calls this out as critical because often no single party has complete control or visibility over the entire risk at that boundary. Safety can literally fall into the gap between organizations.
Right. And you mentioned that staggering statistic, the platform train interface alone accounting for nearly half the passenger fatality risk sometimes. If an interface like that flags high risk, What specific tool or document does a safety plan then demand to make sure the organizational side is managed, not just the tech?
Great question. That's where you typically see the requirement for an interface hazard analysis, or IHA, and its output, the Interface Safety Requirement Specification, or ISRS. If the initial impact assessment flags high interface complexity, it will mandate creating these documents. They force you to explicitly define who is responsible for what at that boundary, what the communication protocols must be, what the safety handshakes are. It makes accountability completely clear, often needing formal sign-off from all parties involved for each defined interface.
Okay, so the triggers point to the problems. Then step 3 is using the criticality matrix to actually quantify this and assign a rating.
Correct. The criticality matrix is basically a simplified risk matrix tool. You plot the likelihood of a hazard occurring, usually categories like unlikely, possible, likely against the consequence if it does occur, insignificant, major, catastrophic. The aim is to visually map out which combinations fall into the unacceptable or critical zone. For example, if potential failure is rated as possible in likelihood and its consequence is catastrophic, that combination lands squarely in the critical zone. No arguments.
And governing this is the critical rule. Let's just hammer home why that rule is so important.
The critical rule really embodies that conservative approach we talked about. It states, if any single identified risk in the project scores as critical on that matrix, like possible catastrophic or maybe likely major, then the entire project is deemed critical. The logic is straightforward. You have to resource the project to handle its highest level of risk. You can't manage a project with one potential catastrophic outcome using the same lightweight process you'd use for a project with only minor risks. If even one part of the system needs, say, SIL 4-level safety integrity, then the whole project management framework, the whole SMEP, needs to be elevated to match that level of criticality, often called C4. This ensures the necessary rigor, the right procurement controls, the highest level of management attention is applied everywhere it needs to be. Now, some more sophisticated organizations might use graduated criticality scales, maybe C1 to C4, allowing a bit more nuance, C1 being low criticality, C4 being the maximum. But the core principle is the same. The project as a whole inherits the criticality rating of its most critical element.
Got it. The weakest link determines the strength of the chain, essentially. So once you have that definitive C rating, C1 to C4, how does that immediately translate into specific engineering work? That's step 4, allocating safety assurance tasks.
Right. The criticality rating directly dictates the mandatory scope of work within the System Safety Assurance Management Plan, SSMP. Specific safety tasks are assigned based on this rating. For a highly critical project, say C3 or C4, you're mandated to use the heavy-duty safety engineering tools, things like formal hazard identification studies, maybe a HAZ workshop or a more detailed HAZOP. You'll definitely need to do failure mode, effects, and criticality analysis, FMECA, and fault tree analysis, FTA, to model how failures can combine. And crucially, for electronic systems, this step includes determining the required safety integrity level, or SIL, for any safety functions. That's the quantifiable target for how reliable those critical functions need to be.
Can you just briefly explain what FMECA actually produces? What's the output for the team?
Sure. FEC is incredibly systematic. You basically take a subsystem like a braking unit or door control module, and you break it down. For every single component, a relay, a sensor, a valve, even a line of code, you ask, how could this specific thing fail? That's the failure mode. Then what would be the immediate effect on the subsystem and the wider system if it failed in that way? And finally, you assess the criticality of that effect. How severe is the ultimate consequence? This detailed bottom-up analysis feeds directly into understanding the system's weaknesses and calculating its overall reliability. And the fundamental rule when allocating these tasks is accountability. Any standard SSA task like a HAZOP or FMECA that the project decides not to undertake. That decision has to be formally justified in writing, approved by the chief engineer, and meticulously documented in the project's safety case. You can't just skip a HAZOP because you're short on time. You need a watertight, regulator-approved reason. If there's any uncertainty about whether a task is needed, the default instruction is clear. Include the task. It's far easier to justify scaling back an effort later if it proves unnecessary than it is to fix a safety gap discovered because you skipped a crucial analysis early on.
Okay, so the criticality assessment sets the overall level of rigor needed. And you mentioned that for those higher criticality projects, C3 or C4, it often triggers the need to determine safety integrity levels, SIL. SIL is a term many of our listeners might have heard but maybe aren't totally clear on. Can you explain exactly what SIL is and where it fits into this whole safety picture?
Right. SIL, safety integrity level, is essentially the quantitative measure of reliability for safety functions. Think of a safety function as something specific the system does to prevent harm, like the automatic train protection, the ATP system, that automatically breaks the train if it passes a red signal. SIL quantifies how reliable that specific safety function needs to be. It sets a target level of risk reduction that the function must achieve. So it's the technical bridge that takes you from the broader, more qualitative criticality assessment of the project to specific, verifiable design requirements for critical functions within that project. It's all designed in international standards, primarily IEC 61508 for general functional safety, and then specialized for railways in EN 50129.
And it's a scale, right? What do the different levels mean?
Yes, it's a scale from SI1 to SIL4. SI1 is the lowest level. It applies to functions where failure might lead to minor injury or maybe significant economic damage, but not catastrophe. Reliability needs to be good, but not extreme. SIL2 requires a higher level of safety performance. You might see this for things like depot protection systems or maybe safety functions related to new energy sources like hydrogen on trains, moderate risk, high reliability needed. SIL3 is for high demand or continuous control functions where failures have serious consequences, potentially severe injury or death to a small number of people. The system needs very high reliability and availability. And then SIL4, that's reserved for the most critical functions where failure could lead to multiple fatalities, a catastrophe. This is the domain of core signaling interlockings, the main ATP systems, maybe critical level crossing controls. Failure at SIL4 is considered intolerable.
So the criticality assessment might say the overall project is C4, and then within that, specific functions like the signaling interlocking get assigned SIL4 target. The process for determining the SIL must be pretty intense.
It is. It's very rigorous and systematic. The basic flow goes like this. First, you do a detailed risk assessment specifically for the safety function in question. What hazard is it protecting against? Second, based on the severity of that hazard and how often the dangerous situation might occur without the safety function, you determine the target SIL required. Third, and this is key, you have to calculate the system's actual reliability. For functions that only act when needed, we calculate the probability of failure on demand, or PFD. How likely is it to fail when it's called upon? Fourth, you verify that the calculated PFD for your design meets the target required for that SIL level. If your design doesn't meet, say, the SIL3 target, you have to go back, improve the design, maybe add more redundancy, use more reliable components, add more self-testing, and recalculate until you meet the target.
Okay, probability of failure on demand, PFD. Let's clarify that for the tech folks listening. Why PFD specifically for SIL rather than something like probability of failure per hour, PFH? What's the difference in thinking there?
That's a really fundamental concept in functional safety. We use PFD for what are called low-demand mode systems. These are safety functions that basically sit dormant, waiting until a dangerous situation occurs, and then they have to act. Think of an emergency stop button or the ATP system intervening when a signal is passed at danger. The crucial question for these systems is, what's the probability it fails on the specific occasion we demand it to work? Hence, probability of failure on demand. PFH, probability of failure per hour, is used for high demand mode or continuous mode systems. These are safety functions that are working all the time, constantly monitoring or controlling something, like a system that continuously monitors train speed or a sensor that's always checking track integrity. For those, the relevant measure is how likely they are to fail within any given hour of operation. The SIL standards actually define targets for both PFD and PFH, depending on the mode of operation of the safety function. But PFD is really key for those ultimate protective layers.
That makes sense. Different ways of failing depending on how the system works. Let's bring this back to the real world again, maybe the Middle East context. How did SIL determination play out in the Etihad Rail project?
Okay. Yeah, good example is the Al Fayed Depot protection systems on Etihad Rail. These systems achieved a SIL2 certification. Now that SIL2 rating wasn't just picked out of thin air. It was a direct result of the earlier impact assessment and the specific risk analysis for the depot. That assessment considered the unique operating conditions, the harsh desert environment, high temperatures, dust, which all affects how long components last and how reliably they perform. It also considered the potential consequences of failures, things like accidents involving shunter vehicles in a busy depot environment. Maybe not a catastrophic in the SIL4 sense, but certainly potential for serious injury or major damage. It's definitely significant. And it looked at the system complexity they were using, things like Wi-Fi-based interlocks, RFID tags for vehicle identification, and driver logo. That introduces technology novelty in specific failure modes.
So putting it together, the harsh environment, the moderate but significant potential consequences of an accident, plus the specific tech complexity, That combination pointed towards needing a SIL 2 level of integrity.
Exactly. The risk assessment concluded that the risk reduction provided by SIL-1 wouldn't be sufficient, but the extreme measures needed for SIL-3 weren't warranted. So SIL-2 became the target. And achieving SIL-2 then dictates specific design choices, things like needing certain levels of redundancy in critical components, requirements for fault detection mechanisms, specific testing protocols. It ensures that those key safety functions in the depot will perform correctly between 99% and 99.9% of the time they're needed. And what's really interesting and important to grasp is that as economies develop, like we're seeing across the Middle East, public expectations for safety rise. What might have been considered an acceptable level of risk, say, 20 years ago, might not be tolerated today. This pushes engineers and regulators to demand higher SIL targets over time, reflecting those evolving societal expectations.
Let's stay with that theme of extreme environments and link this criticality assessment process directly to a couple of those major global projects. How did the initial assessment force extraordinary safety measures specifically because of where they were being built?
Yeah, the Dubai Metro is a fantastic example of achieving world-class safety, partly because the criticality assessment was so conservative right from the start, driven by the environment. Remember, this was the Arabian Peninsula's first big urban rail system. So the initial impact assessment had to grapple with environmental factors that systems built in, say, London or New York, just don't encounter.
Can you give us some specifics on those environmental challenges? What did the design actually have to cope with day to day?
We're talking about really hostile conditions. The specifications had to cover ambient temperatures swinging wildly from near freezing, maybe -1°C on some desert nights, up to a blistering 52°C, over 125 Fahrenheit, in direct summer sun. That's a massive operating range for sensitive electronics and mechanical parts. On top of that, you have frequent high winds, sometimes up to 160 kilometers per hour, carrying abrasive sand and fine dust. That creates huge challenges for filtration systems, for keeping components clean, for visibility, and just general wear and tear. And then, particularly near the coast, you've got a corrosive atmosphere with high salt content, which loves to attack metal structures and electrical contacts.
That sounds like an environment actively trying to break the technology. So how did the criticality assessment process react to those factors?
Well, those conditions immediately pushed several of the assessment dimensions toward the critical end of the scale. Technology novelty was a big one. Even proven European systems had question marks over their long-term failure rates when subjected to that kind of sustained heat and dust. Would they perform as reliably? The assessment basically had to classify the whole project as highly critical right out of the gate. And that classification then mandated extensive independent verification and validation, not just of the design itself, but crucially of the reliability, availability, and maintainability standards, the RAM's performance targets. Could the chosen technology actually meet the demanding service levels in that environment? The outcome, achieving that incredible 99.69% punctuality by 2019, which is among the world's best, really validated taking that aggressive, conservative approach early on. The extra resources forced by the criticality assessment were clearly necessary.
It really shows the power of that upfront assessment. And a similar story, maybe with added time pressure, played out in Qatar with the Doha Metro.
Absolutely. Doha faced its own unique pressure cooker of critical factors. You had the fully automated driverless operation itself, complex, running at high speeds, up to 100 kilometers, making it one of the fastest automated systems anywhere. Add in the same harsh desert conditions as Dubai, maybe even hotter sometimes, and then throw in the immense, immovable deadline of the 2022 World Cup. That essentially removed any buffer in the schedule, adding huge pressure. Plus, like Dubai initially, there wasn't a deep pool of local railway safety expertise, meaning heavy reliance on international partners, which immediately adds layers of organizational complexity to manage.
Beyond the environment and the tight schedule, was there a specific technical system that the impact assessment really zeroed in on as critical, especially because of the risk of cascading failures in a fully automated setup?
Yes. One area that got intense focus due to the criticality assessment was the reliability of the power systems. Specifically, the uninterruptible power supplies the UPS systems that back up the signaling and emergency communications. Why? Because in a fully automated driverless system, the signaling system is effectively the brain and the safety guardian. If the UPS supporting the signaling fails, especially under the extreme heat and electrical load during a Qatari summer, you risk a cascade failure. A loss of signaling power could potentially lead to dangerous situations across the network. So the criticality assessment forced the project to adopt very high specifications for the UPS, demand high levels of redundancy, and mandate rigorous independent testing of those power backup systems.
It's really important to stress, though, that while these projects were built in unique locations with unique challenges, they weren't operating under some kind of local, maybe less stringent set of safety standards, were they?
No, absolutely not. That's vital for everyone, especially engineers looking to work internationally, to understand. Major projects across the Middle East, Dubai, Doha, ongoing work in Saudi Arabia, Egypt, they overwhelmingly adopt and rigorously apply established global safety standards. The Sinelic NEN 50126, 50129, 50128 family of standards for RAMs, signaling hardware, and safety software. These are the common language, the foundation. This ensures that the safety processes, the documentation, the evidence required, it's all compatible with the highest international benchmarks. And this trend towards harmonization is only getting stronger, for instance, with the development of the GCC Railways Authority and its integration with global bodies like the UIC, the International Union of Railways. It means safety expectations are converging globally.
Okay, we've got the process, the standards, the real-world application. Let's switch gears slightly and talk about the human side. Even with all these rules and dimensions, where do things sometimes go wrong? What are the common traps or pitfalls engineers, even experienced ones, might fall into when doing these criticality assessments?
Yeah, despite the structured process, there are definitely common pitfalls. One of the biggest is probably premature risk dismissal. This happens when engineers, maybe feeling pressure on the schedule or budget, or perhaps just through professional optimism, classify a potential risk as insignificant or negligible too early, based on incomplete information or analysis. The trap is thinking, this seems minor on its own, and failing to consider how it might interact with dozens of other seemingly minor issues down the line. This directly undermines that additivity dimension we discussed.
So the antidote here is, once again, sticking rigidly to that conservative principle.
Absolutely. Assume the worst reasonable case in that preliminary assessment. Document why you've rated something as potentially significant, even if you hope later analysis proves it isn't. It is always, always better to justify why you allocated safety resources that maybe weren't fully needed. In the end, you can document that as safety margin than it is to explain why a critical hazard was missed because the initial assessment was too optimistic. That conservative mandate acts as a professional shield against pressure to cut corners early on.
Makes sense. Okay, pitfall number 2, you called it the Achilles heel earlier, interface hazard underestimation. Why are interfaces still so consistently tricky, even when we know, for example, how high the risk is at the platform train interface?
They remain challenging because the risk at an interface is often diffused, both technically and organizationally. You have the physical interface, sure, the gap between train and platform, but you also have organizational interfaces, the track owner versus the train operator. You have departmental interfaces, maintenance versus operations. The core problem is that usually no single person or entity has complete control and visibility over the entire risk across that boundary. A maintenance team might make a change to a train system, unaware of how it impacts a platform procedure managed by station staff, and nobody connects the dots until something goes wrong. Responsibility gets blurred. So the best practice, baked into the assessment process, is to be absolutely explicit. Identify every significant interface point in the impact assessment, physical, organizational, technical. Define them clearly. Assess the specific failure modes that can only happen at that boundary. And then, crucially, formally document who is responsible for managing that interface risk and what the coordination mechanisms must be often captured in that interface safety requirement specification we talked about. You have to force clarity on who owns the risk at the seam.
And if the project is deemed critical, especially due to these complex interfaces or high consequences, it often triggers the need for a specific role, the Independent Safety Assessor, or ISA. Can you explain what the ISA does and why they're considered so essential on major projects?
Right, the ISA is a critical check and balance. It's an independent third-party organization, often a specialized engineering consultancy with deep safety expertise, like Ricardo or TÜV or Lloyd's Register, brought in specifically to provide an unbiased expert opinion on the project's safety. They are mandatory for pretty much all major high-criticality railway projects worldwide: Dubai, Doha, Crossrail, HS2, you name it. Their key value is their independence. They have no financial stake in the project's delivery timeline or budget. Their only concern is safety assurance. This independence allows them to ask the tough questions and challenge assumptions without internal pressures.
So what are they actually looking at? What's in their scope when they review a project?
Their responsibilities are quite broad but focused. They perform a thorough review of all the key safety documentation.
The main safety case of the project, the hazard log, the outputs from things like FMECA and FTA, the Sentinel justification reports. They verify that the project is actually complying with the relevant standards, like the CNELEC norms. They don't just check that an AIDS output was done, they assess how well it was done, whether the conclusions are sound. And they often conduct independent audits and site inspections to see if the safety practices described on paper are actually being followed in reality. Having an ICIT involved isn't just about ticking a regulatory box. It sends a powerful signal about the project's commitment to safety rigor.
And all this work, all these assessments and reviews ultimately feeds into one central document, right? The hazard log. You called it the living document.
Yes, the hazard log is absolutely central. It's the definitive, auditable record of every single hazard identified on the project, how it was assessed, what controls were put in place, who's responsible, and what its current status is. A good hazard log has a clear structure, a unique ID for each hazard, a clear description, its potential causes, its consequences, the specific control measures applied, who owns the action, and whether the hazard is considered open, closed, or maybe transferred. It's the project's safety memory. And there was one absolutely crucial rule for managing this log, something every safety professional needs tattooed on their brain. Hazards should never simply be deleted. If a risk becomes irrelevant, maybe the design changes or a component is removed, you don't just hit delete. You formally close the hazard entry. You provide a clear justification, maybe out of scope due to design change, or risk-reduced LARP and documented in Safety Case Section X, or eliminated by redesign over that. But the original entry, the history, remains in the log. It must be a living document that accurately reflects the entire safety journey of the project, warts and all. This preserves the audit trail and ensures full accountability, sometimes years later.
Okay, we've talked about identifying critical risks and putting controls in place, often involving significant resources thanks to that initial assessment. But inevitably, there's always a point where you hit budget limits or time constraints. How is that fundamental tension between achieving absolute safety and practical limitations managed legally and professionally?
That tension is addressed through a core legal and ethical principle known as so far as is reasonably practicable, or SREP. You'll often hear the acronym ALARP used as well as low as reasonably practicable. They essentially mean the same thing. This principle provides the regulatory framework. It acknowledges that the duty to ensure safety doesn't mean safety at any cost, regardless of how small the risk is. Instead, risks must be reduced, ALARP. This involves balancing the level of risk against the sacrifice, the time, trouble, cost, and effort needed to reduce it further.
That sounds like it could be a bit of a loophole, though, a way to justify not spending money if a safety measure is expensive.
It can be misused, which is why regulators scrutinize ALARP justifications very carefully. The key word is reasonably. For a risk to be considered ALARP, the cost or difficulty of implementing further safety measures must be grossly disproportionate to the safety benefit gained. Think of it like a triangle. At the top are intolerable risks that must be eliminated or reduced, almost regardless of cost. At the bottom are broadly acceptable, negligible risks. In the middle is the tolerable region where risks must be reduced, ALARP. But, and this is the absolutely critical point for engineers to understand, simply not having the budget allocated or being behind schedule is generally not accepted as a valid reason for arguing that a safety measure isn't reasonably practicable, especially for significant risks identified as critical early on. If the criticality assessment flags a high risk, the law effectively mandates proportionate investment to bring that risk down into the tolerable or acceptable region. You have to demonstrate you've done everything reasonably practicable and document why any remaining residual risk is LRP.
That's a crucial clarification. The assessment forces the reasonable spending. Okay, let's shift focus one last time and look ahead. What emerging trends or changes do you see on the horizon that will force railway safety professionals to adapt how they even think about impact assessment and criticality?
I think there are three big ones shaping the future. First is the relentless march of digitalization and predictive analytics. We're moving away from just reacting to failures based on historical data towards proactively predicting failures before they happen. Think about organizations like the MTA in New York using big data and machine learning algorithms, analyzing real-time data from sensors on trains and track to predict when a specific component is likely to fail.
How does that change the input for something like the criticality matrix we discussed? Does likelihood become dynamic?
Exactly. It fundamentally changes how we assess dimensions like novelty and even likelihood. Instead of a component having a fixed RIRL level, predictive analytics introduces a sort of dynamic criticality. The assessed criticality of an asset could actually increase in real time if its predictive health monitoring indicates its probability of failure is rising sharply, maybe due to unexpected wear or a change in how it's being used. This implies that the impact assessment might need to become less of a static upfront project document and more of a continuous living assessment throughout the asset's entire lifecycle, constantly updated by real-time data. The second major trend links directly back to those Dubai and Doha examples, climate change adaptation.
Right, designing for the new normal of extreme weather.
Precisely. Those environmental extremes we talked about in the Gulf, the huge temperature swings, the intense dust storms, they might have been considered once-in-a-lifetime outliers in other parts of the world. Not anymore. As climate patterns shift globally, future impact assessments everywhere will have to seriously consider and incorporate environmental extremes that were previously dismissed as highly improbable. If heat waves, intense rainfall, flooding, or wildfires are becoming more frequent or severe in a region, then our assessment of failure consequences and likelihoods for infrastructure resilience must be adjusted upwards. This will inevitably drive higher criticality ratings for projects and force greater investment in adaptation measures. And the third trend is that continued drive towards harmonization of standards and practices globally. We mentioned the integration of bodies like the GCC Railways Authority into the global framework. This signals that regional projects will increasingly adhere to consistent international criteria for things like criticality assessment and SIL determination. While this standardization is great for sharing expertise and ensuring baseline safety levels, it also means less flexibility to perhaps lower certain requirements based on purely local interpretations. The global benchmark becomes the expectation. So when you pull it all together, that initial impact assessment, the criticality matrix, the hazard log, they really form the invisible architecture that underpins the safe operation of all that visible railway infrastructure we see. Every safe passenger journey, every train running on time, every system performing reliably even under stress, you can trace the success back to those early, often conservative, decisions made during the impact assessment about what risks demanded the most attention and the necessary resources.
It really highlights the importance of getting that foundation right. So for our listeners, especially the engineering students or those just starting their careers in rail safety, what are the key practical takeaways they should keep in mind from this deep dive?
Okay, 4 quick things. First, master the standards. Get familiar with EN 50126, EN 50129, IEC 61508. They represent decades of hard-won industry knowledge. Read them, understand them. Second, always be conservative in those early assessments. Assume the worst plausible case when in doubt, and be ready to rigorously defend the resulting need for safety resources against inevitable pressures. It's your professional duty. Third, focus disproportionately on interfaces. That's where technical, organizational, and human factors collide, and where risks often hide in plain sight. Challenge assumptions about how systems and teams will interact. And fourth, treat your documentation, especially the hazard log, as critical evidence. It must be thorough, transparent, auditable, and maintained meticulously as a living record. It's your proof of due diligence.
Excellent advice. And as that 2024 battery fire in Dubai reminded us, this process of assessing criticality is never really finished. New hazards constantly emerge from technology, from society, from passenger behavior. Which brings us to our final provocative thought for you, the listener, to mull over.
If the core job of safety assurance is to anticipate and control failure, but modern technology, think about AI starting to appear in control systems, or new types of portable energy devices passengers bring on board, is evolving much faster than standards or regulations can possibly keep up. How do our fundamental assessment frameworks, like the criticality dimensions we discussed, need to evolve? How do we tackle the criticality of hazards arising from technologies and behaviors that we can barely even anticipate today? Should we be thinking about adding new dimensions like behavioral novelty or maybe even regulatory lag to our assessments?
That is a huge and vital question for the future of railway safety, something for all of us to think about. Thank you for guiding us through the absolutely critical world of impact assessment and safety assurance today. Until next time on The Deep Dive, keep digging deeper.
Thanks for listening to Safe Tracks, the Systems Safety Assurance podcast. Here, we talk all about how safety assurance keeps our railways running safely, smoothly, and reliably every single day. If you're curious about RAM management, RAM analysis, and how reliability is actually calculated, check out the RAMs Ready podcast playlist on this channel. It's packed with great insights. And hey, don't forget to subscribe and tap the notification bell so you'll know the moment a new episode is out. Until next time, stay safe, stay assured.